Let's get back to work. Session 2.2. In this session, we will turn our attention to the basic concepts of linear power supplies. Linear power supplies is subject outcome 1.5 of the Level 3 curriculum, but we will also be incorporating measuring instruments, subject outcome 1.1, and semiconductor diodes, subject outcome 1.3. You can also link subject outcomes together in this way when teaching your students. All circuits require some source of power to operate. The most convenient source of such power is alternating current, which is easily obtained from any AC socket outlet. Remember that AC current is current that changes direction many times a second at regular intervals. In South Africa, it changes direction 50 times a second, or 50 Hz. The waveform is usually a sine wave and is represented like this. Unfortunately, most electronic circuits and equipment cannot make use of AC directly and therefore must be converted to direct current, DC. Direct current flows through a circuit in one direction only and is represented by the following graph. The process of changing AC to DC is called rectification. The following circuits will be discussed in this session. Half-wave rectifier circuit, 1 diode. Full-wave rectifier circuit, 2 diodes and a center tap transformer. Full-wave rectifier circuit, 4 diodes and a standard transformer. Diodes have many applications, but for this session, we will only examine its use as a rectifier. Simply put, rectification is the process of converting alternating current, AC, to direct current, DC. This involves the use of a device or component that will only allow current to flow in one direction. This is exactly what a semiconductor diode does, because it conducts when it is forward biased and it does not conduct when it is reverse biased. Let's first consider a half-wave rectifier circuit. The operation of a half-wave rectifier circuit is quite simple to understand. The input waveform is a sine wave, which represents an alternating quantity of voltage or current. During the positive half cycle of the input wave, the diode, which is connected to point A on the secondary side of the transformer, will be forward biased. It will therefore conduct and current will flow from point A through the diode, the load resistor, and then to point B of the transformer. During the negative half cycle of input wave, the diode will be reverse biased and will not conduct at all. Because the diode passes current only during the positive half cycle of the input wave and not the negative half cycle, we get the waveform as shown at the output, which is the load resistor. Only the positive half of the input sine wave is present at the output. The negative half has been removed. This process is called half-wave rectification. Let us now watch a video to show the circuit in action.
What we are about to see now is a process called rectification. Rectification in essence means converting alternating current, which is represented by a sine wave, into direct current, which is represented by a straight line. You saw that when we connected a 9-volt battery, it was a straight line. Our ultimate aim is to get a waveform that is not a sine wave, but a straight line wave. But there is a process that needs to be followed. The first part of the process is called rectification. There are 3 variants of rectification. One is called half-wave rectifier, where we use just 1 diode, as you can see there. And remember what a diode is. A diode is a component that only allows current to flow in one direction only. That is what we're looking for at the end of the day when we're talking DC. DC stands for direct current. AC stands for alternating current. Current that changes every so often. Now I've taken one winding from my center tap transformer. I've connected it to the anode of my diode. I've taken my common line and I've connected it to my oscilloscope, and I've taken this is now DC, but it's not the DC we're looking for. It's not a straight line. It's a pulsating DC. The term we use is called pulsating DC. As you can see on the oscilloscope, this is pulsating DC. As you can see with the half-wave rectifier circuit, that means using just one diode, we have now lost the negative side of our sine wave. Remember, sine wave was going like that, going down and coming up. So the diode, because it's forward biased, it's now conducting. But in the negative half cycle of the sine wave, it's not conducting because it's now reverse bias, and you get a gap here. This gap is critical because now we are wasting energy. At this point in time, the power supply is not generating any energy at all, which makes the half-wave rectifier circuit very, very inefficient. So there must be another way that we can try and improve on this design. A half-wave rectifier you will find still in circulation with very cheap imported perhaps equipment. They still use it, but it's very troublesome and it gives a lot of interference in household appliances like televisions and radios that will end up with a hum on the speaker and so forth. It still works, it's still rectified, however we are wasting a lot of energy, as you can see by this. The other thing that you must also take cognizance of is that the frequency remains 50 Hertz. I've explained to you that this is going to give us our frequency. We don't have to go and count the graticals anymore. So you can see a half-wave rectifier, the waveform that it presents is exactly as you see it on the oscilloscope screen at the moment.
Now let's have a look at a full-wave rectifier circuit. A full-wave rectifier circuit is one that rectifies both the positive and negative cycles of the input alternating quantity. In this particular example, 2 diodes and a center tap transformer are used. You can see on the circuit diagram that the input waveform is a sine wave, which represents an alternating quantity. During the positive half cycle of the input wave, diode D1 will be forward biased and D2 will be reverse biased. D1 will therefore conduct and current will flow from point A of the transformer through D1, then through the load resistor and back to point C of the transformer. During the negative half cycle of the input wave, diode D2 will now be forward biased and D1 will be reverse biased. D2 will now conduct and current will flow from point B of the transformer through D2, through the load resistor, in the same direction as before, to point C of the transformer. From this, we can see that current flows through the load resistor in one direction, only for both AC half cycles, so the full AC wave cycle is used. The output waveform that is obtained is shown here at the load resistor. This process is called full wave rectification, and AC has been changed to DC. Let us now watch how this circuit would be constructed on a breadboard.
What we have here on the breadboard is a representation of a full wave rectifier circuit using the same center tap transformer. However, we are now using 2 diodes as opposed to 1 diode when we did the half wave rectifier. Let's see how it's connected. Our center tap forms the earth electrode. One end of my secondary winding goes to the anode of 1 diode. The other end of my transformer secondary winding goes to the anode of another diode. Both the cathodes are joined together and our output is then taken from that point. And notice what happens to the waveform now. Also take particular notice as to what happens to the frequency when we are using a full wave circuit like we are seeing now. So this circuit represents rectification. The type is full wave using a center tap transformer. This is the waveform that is represented by a full wave rectifier that is using 2 diodes, and as we have explained before, we are using a center tap transformer. You could use a standard transformer and you'll get exactly the same waveform. Look what's happened to the frequency. The frequency has now doubled from 50 to 100 hertz. So already we are getting a slightly higher frequency power supply, which makes it efficient, number one. Number two, the positive half cycle for each part of the sine wave is now used. If you look at my fingers, you will see that. There's no more gap here like you saw with the half wave rectifier. Each part of the sine wave, the positive half cycle and the negative half cycle, is being utilized, which makes it a very efficient power supply. All we need now is to remove these things called pulsating DC. This is called pulsating DC. We need to get rid of that. We need to now make it a straight line DC like we saw with the battery that we used. And the only way to do that is to add in filtering circuits where we use capacitors. If you want to get into a more efficient filter circuit, we'll use capacitors and inductors, but it's beyond the scope of this course. So we're just going to use a single capacitor to see how we can remove these peaks, if you like to call them, into a straight line graph, and that's what we are actually looking for. So that waveform is representing a full wave rectifier using 2 diodes and a center tap transformer.
There is another type of full wave rectifier that your students need to be familiar with. It is called a bridge rectifier circuit, and it uses 4 diodes and a transformer. During the positive half cycle of the input wave, diode D1 and D2 will be forward biased, and D3 and D4 will be reverse biased. D1 will therefore conduct first, and current will flow from point X of the transformer to point A, then to point B through diode D1, through the load resistor to point D, through D2 to point C, and then back to point Y of the transformer. During the negative half cycle of the input wave, diode D3 and D4 will now be forward biased, and D1 and D2 will be reverse biased. D3 will then conduct first, and current will flow from point Y of the transformer to point C, then to point B through diode D3, through the load resistor to point D, through D4 to point A, and then back to point X of the transformer. Current flows through the load resistor in the same direction for both cycles, so it is once again called full wave rectification, where alternating current has been changed to direct current. You will have noticed that although the rectifier circuits we have just discussed produce direct current, the output waveforms obtained are not a straight line. This is not ideal because in order to power equipment, the power source needs to be as stable as possible, as it would be if you were using a battery. In order to get a straight line waveform, filters and regulators must be added to the circuit. The simplest filter that can be added across the load is an electrolytic or polarized capacitor, usually in the range of about 2,200 microfarads or higher. This will give us the required waveform but with a small ripple, which is acceptable for most applications. Using a capacitor in this way is known as smoothing or filtering.
We are still with a full wave bridge rectifier circuit with 2 diodes. But as you can see on the display on the oscilloscope, we have still a pulsating DC. We need to, as we've discussed, remove these peaks, which we call a pulsating DC. And we do that quite simply by adding a capacitor. Notice the waveform changing to a straight line. That's what we are aiming for the moment you add a capacitor. I'm using a 2,200 microfarad capacitor rated at about 63 volts. You just need to have the voltage. The voltage is critical. If you are working with a power supply that's going to exceed 100 volts, then you have to have a capacitor that will exceed 100 volts as well. That's called the working voltage. Notice the waveform changing into a straight line the moment I add a filter. That's what we're looking for. If I remove my filter, I'm back to my pulsating DC. If I add a filter, I get a straight line. From here on, all you have to do is add a voltage regulator of your choice. If you wish to have a power supply that's 9 volts, you add a 7809 voltage regulator. If you wish to have a power supply that's 12 volts, you just add a 7812 voltage regulator. If you're looking to have a negative voltage, which operational amplifiers require, then you'll use a series called the 79 series. For positive regulation, you require the 78 series. For negative supplies, you require the 79 series.
Once the waveform has been smoothed, the output voltage of power supplies must be regulated to produce exactly what the equipment requires. For example, 12 volts, 5 volts, 24 volts, and so on. AC voltages from the main supply fluctuate quite a lot, and this affects the output of power supplies to a great extent. This means that some form of regulation is always required, especially for sensitive electronic equipment. Zener diodes can be used for this purpose, but they are limited in the amount of current they can deliver. 3-terminal linear fixed voltage regulators are therefore a popular choice for creating either positive or negative supply voltages and are used on most equipment. Common types include these listed here. These are positive voltage regulators, where the last 2 digits indicate the output voltage. The 79 series are negative voltage regulators. Let's now look at how a voltage regulator is connected to a power supply circuit. The voltage regulator has 3-pin connections, and they are connected into the circuit as shown here. Here are the components of a typical linear power supply and how they are connected. Note how the waveform changes from AC to DC with each step. We will now watch a video in which a voltage regulator is added to the circuit, completing the linear power supply.
We have now added into the circuit a 12-volt regulator. This pin is in, which means it comes in from where your 2 diode cathodes meet, or where the positive of your capacitor is connected. The center pin is your common pin. The last pin, the 3rd pin here, is your output. If I connect my output to my multimeter like so, and if I connect my common, which is common to everything here, like so, and if I power up on my multimeter, I should see a nice 12 volts or very close to 12 volts DC power supply. And that is the completion of the power supply circuit. If you construct this on Vero board very nice and neatly, you would have a 12-volt power supply which you could use to charge batteries. You could use it to charge your cell phone. You could use it to do anything. You could use it to run your radio. You could use it to run a small TV. It is a fully functional power supply that you could make on your own and that you could use for various applications as and when you wish to. So this is the whole circuitry that we've discussed as regards the linear power supply.
We are now going to get some practical experience by building your own linear power supply, in the same way as it was done in the videos you watched during the session. Your facilitator will provide you with a breadboard and the necessary components. Refer to your workbook for instructions on this practical activity. End of Module 2.